Okay, now let's see another lemma. That is, let's say H is a subgroup of G, and in addition, we assume that H is a finite subgroup. Okay, it's not just any subgroup, it's finite subgroup. This is important. Then for any A in G, the the number of elements in a coset of H is equal to the number of elements of H. Okay, so this is the lemma. So we want to prove this. To prove this, we define a mapping from H to HA. Okay, so A is any element of G, and we show that this mapping F is a bijection. Okay, we show F is a bijection. So if H is assumed to be a finite set, so if there's a bijection between H and HA, that means the number of elements in HA is the same as the number of elements in H. Okay, so this F is defined by this, just HA, and of course H is an element of H. Okay, so this is how we define this mapping. Okay, and clearly F is a surjection. Surjective. So this means if we pick any element in H, so that means for any element in HA, there maybe we should write Y. There exists X in H such that f of X is equal to Y. Okay, so if this is satisfied, F is surjective. In other words, so if we have two sets, so every element in HA, if we pick one, then there is a corresponding element in H. So there is nothing, the mapping is misses in HA. Okay, so every element here has some corresponding element in H. Okay, so that's what this means. So this is clear, right? Because this is HA. So since it's a form of H times A, where H is an element of this subgroup H, then this is obviously an element of A. So that means for, any element of HA has this form. So from here, we can find element H such that f of H is equal to HA, right? So this H is in H. So therefore, this is F is surjective. Now, in order to show F is a bijection, then we only need to show, so it's surjective, so we need to show it's injective also. Okay, so suppose f of H1 is equal to f of H2. Then this means H1A is equal to H2A, right? But A is an element of a group, so we can multiply A inverse from A inverse from the right. So that is H1E, H2E. So H1 is equal to H2. Okay, therefore F is injective. Okay, so this means uh, if if two elements in here are different, then they are sent to different elements in HA. Okay, if they are same here, they come from the same point. Okay, so there's nothing like something like this. So no two different points are mapped to the same point. So this doesn't happen. So what this injective means. Okay, therefore F is a bijection. Okay, since it's a bijection, that means the number of elements in H and HA are the same. So in other words, it's one-to-one and onto mapping. Okay, based on this lemma, let's prove the next theorem that is a very famous theorem in group theory called Lagrange Theorem. Let's see. Lagrange. Okay, so let H be a subgroup of G, where G is a finite group. Okay, so be careful. This is applicable to the case where G is a finite group. Then we have this. Okay, so that means the number of elements in H is a divisor of the number of elements of G. And as we have defined before, this is the index of H in G. Okay, so this holds. So let's prove this. Suppose, by the way, since G is finite, this is also finite, right? So suppose the index of H in G is n. So this means G can be written as a disjoint union of n cosets. So there are n cosets, but each of these cosets has the same number of elements. That is H, same as the number of elements in H, right? So that is HA1. So the order of HA1 is equal to HA2, and these are all equal according to the previous lemma. So this means, and they are all disjoint, right? So the order of G is H plus plus, and so these are n terms. So that is n times the order of H, but n is equal to this. So that's it. And we are done. Next, consider an application of this theorem. Say we have two subgroups, H and K. Okay, these are subgroups. And furthermore, we assume that H is a subset of K. Okay, and of course, K is a subset of G. And in this case, by Lagrange theorem, we have G colon H. The order of H is the index of H is times the order of H is equal to G. But if we apply the same theorem to this K, then we have this is equal to G K and K. And if we apply the theorem to this part, so H is a subgroup of K, right? So then we have this K is equal to K colon H times H. So if we substitute this into here, we have G colon K times K colon H and H. So cancel this H here and here, left and right, we have G colon H. So the index of H is equal to the index of K in G times the index of H in K. Let's see a few examples. Example 1. Suppose the order of group G is P, where P is a prime number. In this case, the only subgroups of G are either G or this trivial subgroup consisting of only the identity element. Okay, these are the only possible subgroups of G. To see this, suppose H is a subgroup of G. Okay, then by Lagrange theorem, the order of H divides the order of G, right? But this G is the order of G is a prime number, so therefore the order of H can be either 1 or P. So if this is the case, then the subgroup is this one, and if this is the case, then the only subgroup is G itself. And we have the next example. We have seen this dihedral group of order 8 called D4 many times, and we have seen there are various subgroups, but the orders of these subgroups are either 1 or 2 or 4 or 8. And the subgroup of order 1 is of course this, and the subgroup of order 8 is D4 itself, and the subgroups of order 2 were let's see, it was ED and EG and EF and EH, and the subgroups of order 4 were E, A, B, C and E, B, D, G. And there's one more. E, B, F, H. Okay, next consider the set of integers with addition. Okay, so this is a group. So this is additive group, and we can define a subset of of integers. Let's write it 6z, which is the set of multiples of 6. Okay. Then we can consider a right coset of this subset. So since this is additive group, we write coset as this. So 6z plus a. So in this case, the group multiplication is actually addition. Okay, so that's why we use this plus here. So this coset is defined as this 6x plus a, where x is integer. Okay, of course a is an integer. Okay, and as we have seen before, a and b belong to the same coset. Let's call it a. If and only if the coset 6z plus a is equal to 6z plus b. And also this means a minus b belongs to 6z. So this is, in our previous notation, this would be written as this. A times b inverse belongs to the subgroup. Okay. But here it is additive group, so b inverse is written as minus b. Okay. Of course, minus a minus b means a plus minus b. Okay. So this is abbreviation of this. Okay, and this subgroup H is 6z in this case. So what this means is, okay, so a minus b belongs to 6z means that this means 6. So a minus b is a multiple of 6, so that means 6 divides a minus b. Okay, so actually in this case there are only 6 cosets. That is 6z and 6z plus 1, 6z plus 2, 6z plus 3, and 6z plus 4, and 6z plus 5. So this can be thought of classification of integers based on the remainder when divided by 6. So remainder 0, 1, 2, 3, 4, 5. And in this way we can divide all integers into 6 classes.